Let's be honest, solving systems of differential equations can get pretty messy. But what if I told you there's a way to turn a really tricky calculus problem into a much friendlier algebra problem? Well, that's exactly what the Laplace transform does. And in this explainer, we're going to show you exactly how to use this amazing mathematical tool. So let's dive right in.
Okay, so just take a look at this. On the left, you've got a system of differential equations, a total calculus headache, right? And on the right, a system of linear equations. That's just good old algebra. So which one looks easier? Yeah, it's not even a contest. The whole point of the method we're talking about today is to magically turn that monster on the left into the simple puzzle on the right.
And that really is the big idea here. You can think of the Laplace transform as a kind of universal translator for math. It takes a problem that's super hard to solve in its native language of calculus, with derivatives and all that, and translates it into the much, much simpler language of algebra.
And this really gets to the heart of it. By applying this transform, we're basically shifting our problem from the time domain, where t is our variable, into something called the S domain. It's like a parallel universe for math where derivatives don't even exist. And in this new space, our calculus problem just becomes a straightforward algebra problem that we can solve with tools we already know, like substitution.
Now, the best part about this is that it's not some crazy 50-step process you have to memorize. Nope. It's a clean, repeatable 3-step method. Think of it like a roadmap. Once you learn it, you can follow it every single time to get to the right answer.
So here are the steps. It's pretty simple. First, you transform every single piece of your system into the S domain. Second, you solve that new algebraic system for your variables. And third, you do the inverse transform to translate your solution back into the language of calculus. So transform, solve, inverse. That's the whole game plan.
All right, enough talk. Let's actually put this into practice with a real example. We're going to start, of course, with step 1, taking our system of equations and hitting it with the Laplace transform. So check this out. Here's the before and after. On the left, that's our original system, along with our starting points, our initial conditions. Then on the right, you can see what happens after we've applied the Laplace transform rules. The derivative, x prime, becomes s times a capital X minus the initial condition, and so on. We just plug in our numbers, and just like that, poof, the calculus is gone.
And now for step 2. We've done the transformation, and we've landed in our happy place, the S domain. This is where it's all just algebra. So let's get to solving this thing.
So the very first thing we're going to do is just a little bit of housekeeping. We're going to gather all the capital X terms and all the capital Y terms together for each equation. You can see how this little bit of tidying up puts our system into a nice, standard format that's way easier to deal with.
From here, you can probably see where this is going. If you look at that first equation, it is incredibly easy to get y all by itself. This is just a perfect setup for our old friend, the substitution method. And here it is, the key move. We take that expression for y, and we plug it right into the second equation. The second we do that, the variable y is totally gone. We're left with just one equation and one unknown, capital X.
So after a little bit of algebraic shuffling, factoring out the x and dividing, we get our solution in the S domain. Now this is awesome. This is our transformed answer. But we're not quite done yet. We still have to translate this back.
And that brings us to the home stretch, our final step. We've got to take this algebraic answer, x of s, and use the inverse Laplace transform to find our real solution, x of t. It's time to translate back.
Okay, but hold on. Before we can take the inverse, we have to prep our function a little bit. The way our x of s looks right now is too complicated to just find on a standard transform table. So we've got to use this algebra technique called partial fraction decomposition. It's what lets us break one complicated fraction into several simpler ones. Now, I'm telling you, for a lot of students, this is the trickiest part. So this is a great place to slow down and double-check your algebra.
So once you do the partial fractions correctly, our x of s looks like this. And this is exactly why we did all that work. Each of these simpler fractions, the 1 over s minus 1 and the 1 over s plus 2, are standard forms. We can look them up directly in our Laplace transform table.
So we take the inverse transform of those simple pieces, and we get our final answer for x of t. That's it. The inverse of 1 over s minus 1 is just e to the t, and the inverse of 1 over s plus 2 is e to the negative 2t. And boom, there it is. We have our solution. And notice, we never had to mess around with finding those arbitrary constants like c1 and c2.
So after going through all that, you might be thinking, okay, cool, but why?
Why should I use this method over others I might know, like using eigenvalues?
Well, it turns out there are some huge advantages. First off, it takes care of the initial conditions right at the beginning. They get baked right into the algebra. That means no solving for constants at the end, which is a huge time saver. It's also way better for problems where you have things that are turned on or off at certain times. And honestly, for a lot of these initial value problems, it's just a more direct, less error-prone way to get to the answer than the whole eigenvalue method.
All right, so we have walked through the theory and a full example of this super useful technique. You've seen the three-step method in action. Now it's your turn to put that knowledge to the test. You have the roadmap now. Transform, solve, inverse. And look, the only way to really get this down is to roll up your sleeves and practice. So take what you've learned here, try out the practice problems, and see for yourself how powerful this method really is. Thanks for watching.